Solution of Bessel's equation. So we can obtain solution of Bessel's equation using Frobenius method. We already discussed that Frobenius method. Bessel equation is, differential equation is x square d square y by dx square plus x into dy by dx plus x square minus n square into y is equal to 0. The equation has regular singularity at x equal to 0. There will be at least one solution, that is x equal to, we can expand this solution as at x equal to 0. We assume a solution like this, that is y is equal to summation over lambda is equal to 0 to infinity a lambda x minus x0 to the power k to the power x minus x0 to the power k plus lambda. At x0 is equal to 0, at x0 equal to 0, this equation become, the solution become y is equal to summation over lambda is equal to 0 to infinity a lambda k plus x to the power k plus lambda. So this is our equation. Then we can differentiate this equation, that is dy by dx, equation number 2, and d square y by dx square, equation number 3. So we can substitute this y dy by dx and d square y by dx square in the equation number 1. That is our differential equation. So we will get this equation, this equal to 0. Now what is the method? The first method is equating the, first step is equating the coefficient of lowest power of x. That is, we can put lambda is equal to 0, then we will get x to the power k. Now the coefficient of x to the power k is a0 k into k minus 1 plus a0 k minus n square, a0 is equal to 0. That is a0 into k square minus n square is equal to 0. If the first a0 is not equal to 0, then we can write k square minus n square is equal to 0. That is our integral equation. From this we can find two roots, that is k is equal to plus or minus n. So root is k is equal to plus n or k is equal to minus n. In the case of linear harmonic oscillator, we find that k is equal to 0 and k is equal to 1. The same way, here we find two roots, that is k is equal to, first one is plus n, next one is minus n. Now the second step is, what is the second step? Equating the coefficient of next lowest power, that is, we can put lambda is equal to 1. Lambda is equal to 1 means x, x become x to the power k plus 1. We can this x to the power k, then we will get k square minus n square is equal to 0. That is, when k, okay, this is our equation. When k is equal to plus n, when k is equal to plus n, a1 into 2n plus 1 is equal to 0. That is, a1 is equal to 0. Now we can put k is equal to minus n, k is equal to minus n, then a1 is equal to 0. Okay, so now a1 is equal to 0. The third step is equating the coefficient of x to the power k plus j. That is, we can put lambda is equal to j in the first summation and lambda plus 2 is equal to j in the second summation. Then the coefficient of x to the power k plus j becomes this equal to 0. We can reduce this equation into this form. From this, we can find the recurrence relation aj is equal to minus aj minus 2 divided by k plus j square minus n square. So, and the solution. What is the solution? First one is k is equal to, the roots are, what are the roots? K is equal to plus n and minus n. We got k is equal to plus or minus 1. So we can find the solution for first one is for k is equal to plus n, and the second solution is for k is equal to minus n. So for k is equal to plus n, in the recurrence relation we can put k is equal to plus n, then the equation become aj is equal to minus aj minus 2 divided by n plus j square minus 1. Then the equation becomes like this, aj is equal to this one. When j is equal to j plus 2, when j is equal to j plus 2, the equation becomes aj plus 2 is equal to minus aj divided by j plus 2 into 2n plus j plus 2. This is our recurrence relation. Okay. Now we can find the, okay, we already find that a1 is equal to 0. Anyway, a3, a5, a7, etc. are 0. Then now put j is equal to 0 in the recurrence relation. In the recurrence relation, we put j is equal to 0, then we will get a2. a2 is, we can write like this, that is a0 n factorial minus a0 n factorial divided by 2 square 1 factorial into n plus 1 factorial. Okay. Here we multiplied and divided both sides, means numerator and denominator by n factorial. So here it is n plus 1, n plus 1 into n factorial. That is why here n plus 1 factorial. Okay, now put j is equal to 2 in the recurrence relation, then we will get a4. So we can write a4 because we already got the value of a2 as a0 factorial divided by 2 square 1 factorial n plus 1 factorial. We can put the value of a2 here, substitute the value of here, then we can we will get the value of a4 in terms of a0 like this. Then a6. So in general, we can write a2p is equal to minus 1 to the power p a0 n factorial divided by a to the power p p factorial n plus p factorial. It is the general form. Now the solution is, what is our solution? So, this is factor and cancel, then we will now a2. What is the value of a2? Value a2 already, so that we derived minus a factor by 2 square 1 factor n plus 1 factor. Then this term, that is plus 2. Next is a4. What is the value of a4? a0 and divided by 2 raised to 4, 2 factorial, and 2 factorial n to the power n plus 4. Okay. Right? Is equal to 0 to j n factorial x power n factorial. Okay. So solution is, we write the first like of for minus